And those concepts we will need as the chapter progresses. Not all of them, but some of them. Then we jumped in here, we started talking about properties of energy. Energy has, or there are many different forms of energy that exist, and they can be transferred, or transformed. And we did this chain. We talked about how sunlight can be transformed via photosynthesis into chemical energy that you then change into a different form of chemical energy that you then convert into either motion, sound, or heat. That is the sum total of your existence as it relates to energy transformation. You eat, you release heat, sound, and motion. That's it. Now, the motions that you do and the sounds that you release can have a massive impact on the rest of your life. But that's basically it. There's another way that we tap into sunlight. What's the other way that we tap into sunlight? What's that? That is a solar panel. Does anyone know the name of the piece that we slapped together to make the solar panel? Nobody? Okay. They are called photo for light, voltaic cells. And based on their name, what is their purpose? Photo is relating to light. Voltaic relates to? That sounds an awful lot like what other word? Voltage, which is related to electricity. So the purpose of those cells is to take solar energy, light energy, and turn it into electricity. What is electricity? Oh yeah, you guys don't like that color. Sorry. What's electricity? Come on, Science 9. That was not the right answer. What is electricity? That was Sahib's phone. He forgot to put his earbuds in. That's okay. It's all good. Don't worry about him. Yep, you did for a second. What is electricity, Evelyn? What are the forms of electricity? Of electricity. What are the forms of electricity? You said it depends on the form. Kaylee, what is static? Friction produces static electricity, but what is electricity? Yes. Current. What is current? Oh no, not in the water, because that's not electricity anymore.
Is it like energy?
Okay, all of you made it through Science 9, clear, apparently.
Yeah.
Allegedly. You all in there would have done a unit on electricity.
Yeah.
What is electricity? Did you guys do any labs during that unit? Did you build anything?
Yeah, batteries.
You connected batteries to things?
Yeah, to light bulbs.
What's that thing called when you connect a battery to a light bulb? It's called a circuit. What's the purpose of the circuit? Oh, you're so close. To move the what? Conduct electricity by allowing what to move? What's moving? Electrons. Electricity is just moving electrons. That's all it is. It's allowing electrons a place to flow. That's the whole purpose of the wires when you guys are building circuits. The wires allowed the electrons to go from one to the next and back again. Because if it's broken, they can't go anywhere. You break the circuit, the electrons can't flow. That's a light switch. Breaks the circuit, can't flow, light goes off. And light bulbs turn that electric energy into what? Light, one big key, and what was that? Sahej, was that you? Oh, how dare you! Who broke my rubber band?
Jedediah, it was you, wasn't it?
This was not for you to play with. This was mine. Okay, I'll snap you with a lid. Okay. Light and what? What else does a light bulb produce? Heat. Any of you have an Easy Bake Oven at home when you were a kid?
Yeah.
None of you? Yes, some of you with the Easy Bake Oven. Easy Bake Oven's not a very hot oven, but you were able to cook things with the light bulb inside. So the light bulb has to produce light and heat. Heat's not there, Easy Bake Oven doesn't work. I didn't have the Easy Bake Oven. I had another product of the 90s. My sister got the Easy Bake Oven. I got the creepy crawler oven. It was like, oh yeah, you put like, it was the same kind of cooking trays, but they had molds for different kind of monsters or insects or whatever. And you put like liquid plastic in there and then bake them. And it made little rubber bugs and it was awesome. It was cool. Google it later. Creepy crawler oven. It was very cool.
Can I ask a quick question?
Yes.
Okay, that solar panel thing you're on a walk in the lane is obviously glass.
Okay.
Oh my God, there was a truck parked, okay, just parked, and that exact solar panel was on the front of the dash. What was going on there?
No idea.
Okay, just wondering if it's very thought.
Yeah, don't know.
Is he starting his car with that?
Maybe.
Okay. Yeah.
Maybe. Maybe using it to charge something inside the car.
But that's possible.
Yeah.
That's what I'm asking.
You can buy solar panels that you can carry around in your backpack and set up to charge your phone.
Amazing. Okay.
Coppendale, favorite thing to cook or bake? Steak. Okay. You talk about steak a lot. Okay, so that property is energy. And a simple example of energy transformation. Now, systems. When we talk about energy, we're talking about, we have to narrow our field or enlarge the field so that we're talking about the right area of stuff. We call those things systems. A system is anything under observation. And you, as the observer, get to define what is in your system. We'll use this circle as the example of the system. That's everything that you're focused on. And around the system is, well, what? What do we call everything that's around the system that's not part of your system? Nope. Not necessarily. Could maybe, could be, might not be. It's a little different than in chemistry. In chemistry, we were talking about isolated systems or closed systems versus open systems. In a closed system, the matter was contained, the energy was allowed to come and go. In an open system, energy and matter were allowed to flow. We're not going to talk about closed or open systems. We're going to talk about isolated systems versus not isolated systems. If your system is the area you're observing, what's everything else around you? Not maybe, maybe not. Sorry? No, I thought I heard something else. Starts with an S. I mean, it's also right there. No, it's your system. System's what you're focused on. And then everything else is what are called the surroundings, the aroundness of your isolated, of your observed system. And if you take all the possible systems and all the possible surroundings, you get the ultimate system. What is the ultimate system? If you take every system and all the surroundings, what do you get? Is the atmosphere everything? I don't mean everything, Jedediah. I mean everything. Big, booming, everything voice. Everything. There it is. It's like you guys are not used to people like taking people literally. I am choosing the words intently. Literally everything. The ultimate system. And so what this means is if your system is that big, there is nothing surrounding the universe. The universe is all possible systems and all possible surroundings. There's nothing coming or going. All the energy that exists is already there. And once we use it up, it's gone. If it all gets transformed into the one kind of energy that just kind of disappears forever, then the universe will cease to function. You run out of energy, you die. What about when you die in real life? That's a metaphysical conversation that we're going to not touch here. Well, clearly, never mind. I'm going to take it back. Nope, not going to say that. Okay, moving on from that little detail. We're going to isolate. Okay, we're talking about going from the universe. Let's dial it in a little bit, and let's talk about different kinds of energy. We're going to break up all of the possible energies into either kinetic or potential. And before we talk about kinetics and potentials, let's talk about this word energy here. How do you know if something has energy? It's not like we have an energy meter that you can go up and buzz each other with. But to measure like, oh yes, Evelyn has 6 energy and Sahej has 2 energy. Like, that doesn't exist. So your intuition, we use your intuition all the time to make evaluated judgments on how much energy is present. Yes, Brooklyn. I mean, if it can, then what kind of energy is present? You said if it zaps you. What are you referring to when you talk about zapping? Okay, so have you ever interacted with an electric fence? Okay, you've ever been zapped by one of those things? So you would say that electric fence contains a fair amount of energy. Relate that to, like, I used to, when I was a kid, we'd go to Costco as a family. I drag my feet along the ground. If you've never done this, do this to someone. Drag your feet on the ground in Costco and then sneak up on them and grab their hand. What happens? Has anyone done this? I shocked my mother all the time. She hated it. Yeah, I built up static electricity on me. I'd walk up behind her and I'd grab her hand. Boom, my mom gets a shock. Which one of those contains more energy? The shock that I gave my mother or the electric fence that Brooklyn grabbed? The electric fence has more energy. How do you know that one had more energy? Yeah, same thing when I shocked my mom. But it's stronger. The one that you do to your mom is like, oh, that's annoying. But then the electric fence one is like, that's okay. So the degree to which it hurts you is a useful measure of the amount of energy something has. Absolutely. That's a really simple way to evaluate the energy present in an object. How much will it hurt? And this can be used in all sorts of circumstances. If I am just standing here, I'm just standing here. It's a little weird because, my desk is over there and I often teach from over there and I write down my notes and here I am standing. You might be confused, but really, are you concerned that where I am over here will cause you any sort of bodily harm? I hope not. I hope that as your science teacher, having taught you since February, that you're not concerned that I'm going to hurt you in any way, shape, or form. But what if I started to run at you? All of a sudden, that's more concerning. And I'm not, right? Like, that's concerning to you.
right? Like, what's doing not doing now, he's moving me. And if you don't get out of the way and I tell you I'm just gonna keep going, that would be an uncomfortable set of circumstances. So, there is something to be said. So kinetic. Kinetic is the energy of what? Motion. Kinetic is related, when you think of kinetic, we think of motion. Kinetic energy is the energy of motion. The more energy, so I'll forget that for a second. How do you evaluate without looking at, like there's no meter that I can wear to tell you how much kinetic energy I have. But we evaluate it. So if I'm moving at you, if I'm doing this, as I casually stroll down the hallway at you, is my motion of concern to you? No, but if I run at you, that's a bigger deal. Okay? What if my son and I, actually my son's a bad example. No, my son's a great example. Here's my son, little guy, 2.5, him and I are walking at you down the hallway. Neither of us concern you. Maybe we concern you equally small. But what if my son and I are running down the hallway at you? Which of us is a bigger concern? Me. Why? Even if we're moving at the same speed, and it's not the height, what goes along with the fact that I am much taller than my son? Mass. Mass is the key. I am more massive than my son. He is 30 pounds. I'm 230. I have an extra 200 pounds on him. That alone is the concern. Even with really small things, though, we can evaluate these things. So at home, I don't know if I mentioned this class or not. It came up in my other class. I have a collection of firearms at home, and so as a responsible gun owner, I also have ammunition for my firearms. And if I chose to bring a box of .22 ammunition and just started like clinking it at you, it would be weird. But would it be concerning?
Yes.
No, would you be concerned about your safety as I'm tossing bullets at you?
Yes.
Like, forget the other. Really?
No.
I'm just standing here like, think, fine. You know what? I'll do this. I'll get some thumbtacks and I'm gonna throw them at Severy.
Wow.
Why not?
Yeah.
Okay, here we go, Severy. I picked you because you're wearing a hoodie. I wasn't gonna do it. I'm not gonna throw them at your face, but like these are pokey, right? If I walked up and bam, that would hurt, right? But like, does that hurt? Yeah, they're sharp, right? But does any of this hurt? No. Okay, I'll take those back. Yes, I'm not just gonna out of nowhere bring a box of bullets. That would be okay. Well. Okay, but yeah, there's another one down there somewhere. Watch it goes. Okay, so again, if I just start tossing them at you, not overly concerning. Even if I threw this thing at you as hard as I possibly could, is it really, am I stinging you? But is it really going to do any damage? Any meaningful amount of damage? Does anyone want me to the person to throw? Can I throw this as hard as I can at someone?
Sure.
Sweet, on the wall. I'm glad you volunteered because you're wearing glasses.
Yeah, that's the whole point.
Great, and long sleeves. Fantastic. So, here it is. It would be uncomfortable. I did above your head, you can have a seat. Think for me, right? It's certainly uncomfortable. But would I do any lasting damage to Sarah? No. It would be concerning. No lasting damage would occur. But, and so this is what it, but as soon as I throw, as soon as you throw attack, you guys don't realize this, as soon as you throw attack, it actually turns around.
Yeah.
Because the heavy end is the stable end. So the pointy end wouldn't have hit Sarah. It would have been this flat end. It would have been a little plastic ball. Okay? But, what if, let's go back to my example with the bullets. Bullets, for those of you who don't know what a bullet is, it's just a solid piece of metal. I could bring and I could plink, just like I did at Severy, just like I did at Sarah. I could plink them at you and do no lasting damage. But if we took a field trip and we went and said, okay, we're going to go to the gun range as a field trip, and targets are over there, and I'm shooting at the targets, you're probably going to want to stand behind me. Because that same little bullet placed in the rifle and then trigger pulls, it's the same little piece of metal. Why is it scarier when it comes out the front of a gun? Because it's moving at hundreds of meters per second. And now all of a sudden that same little piece of metal can kill you. But functionally, it's the same little piece of metal. In fact, it's even smaller when it comes out of the gun than if I were to just throw them at you. Empire State Building and no one would get hurt or no one would get killed on the bomb. It would fracture, it might fracture a skull, but it wouldn't kill anybody. So even then, but my point is, like, kinetic energy, your evaluation of whether or not something is going to hurt, yes, it's connected to size, but even more so, it's connected to how fast that object is moving. And your intuition does this. You're like, yeah, that will hurt. And so we can connect that idea to this thing has more energy because it's of how this mass is moving. So that's this first one. Kinetic energy is the energy of motion, and it is related to, and you'll see it when we actually look at the equations for this, you'll see it. It's related to the speed of the object and the mass of the object. So that's the first classification of energy that we're going to talk about. The second is potential. That word potential means what? Has anyone ever told you you have potential?
Yeah.
What does that mean?
Like, it's in you, but it's not out of you.
It means you have the ability to do something great later.
Yeah.
Generally, is that that means.
Like in waterfall.
So kinetic energy is motion right now.
Yeah.
Potential energy is you could exert some energy later. Or if we go back to our definition of how much will it hurt, kinetic is if this moving object hits me, it will hurt. Or not. Or maybe it'll hurt more than other kinds. But you understand that. Like, that's the now. Potential energy is if this thing were allowed to act. You want me to come over there? Okay. If I were to allow something to act, how much would it hurt? Chat amongst yourselves for a second.
Oh yeah, homework. Oh yeah. Not even bad. You will not. I believe it. You got some potential. That's wrong. Don't eat coffee.
Okay, so let's talk about potential. There's different kinds of potential energy. There's different scenarios that I could concoct that I'm going to hold two of them. Potential energies where there exists the potential for something to hurt you later. Here's what I mean. He's not here, so let's use this desk. Is anyone in the class concerned about the presence of the coffee cup or the highlighter? No. As it sits right there, I mean, you might be confused. You might be concerned because what will the weed up? You're saying there's a potential. There's a potential for the weed up to do something stupid. So maybe I should be concerned. But as it sits right now, if those were just sitting on the desk, you might be confused, but you're probably not worried about it hurting you as it sits. But if I this, all of a sudden now this is a little bit more concerning. Because if we connect it to the question I asked you before, how much is it going to hurt? Here, it's not going to hurt at all. Here, it might hurt a little bit more. If I do this versus this, which would hurt more? The higher one, right? So, no, the highlighter, and that's the root of one. Like, what? Yeah, next question. We've established that higher is worse than lower. Which of these is more, if I held one of these over your head, which one of them concerns you more? What about why?
Because it's a big heavy metal.
It's a big heavy metal, and it's full of, and if it's full of water, this thing holds about 3/4 of a liter. And 3/4, so 750 milliliters. 700, the way mass and volume work is that 1 liter of water weighs a kilogram. So this thing, just the liquid, would be 3/4 of a kilogram, never mind the steel and the plastic that go into the rest of this. So we're looking at perhaps somewhere around a kilogram being dropped on Matthew's head versus just the highlighter. The highlighter is nothing, but I won't do that with this. So you've got like, there's the potential, I mean, is it hurting you? Jedediah, are you in pain right now? No. But could you? That would be unrelated. But could you see yourself in pain in a moment if I did something silly?
Yes.
Yeah. So the potential exists for gravity to cause immense pain, depending on the presence or absence of other objects. You said that this one was more concerning than this one because of the difference in mass. You said that higher is worse than lower because the higher something is, the faster it's going to hit, like the faster it will be moving when it finally does get to you. So the last question then is, what if I were somehow able to spontaneously teleport Jedediah and myself to the moon? Forget the fact that that would be awesome. Forget the fact that it would be really cold and we'd have to hold our breath while we're there.
Yeah.
But we'd have a little bit of time to do this.
Okay.
And I could let them go on the moon.
Yeah, I could.
In which location would you be more concerned about bodily harm related to specifically these two objects? On the Earth. Why? Because your understanding of gravity is that it's less on the moon than it is here. Okay. That's gravitational potential. Those three concepts. How the mass and how the height above some level that you reference interacts with the gravity that you're present in. I need one more. We'll do one more of these. The height portion is interesting because the height portion is kind of relative. I need someone willing to sit on the floor. Sweet. Have a seat on the ground.
Right there?
No, like right where your chair is. Push the chair. Don't push the chair to the desk. Push the chair away from you. And I'd like you to sit on the ground. Okay. So, she's even lower than it was before, so this is great. Okay, so, Brooklyn. Brooklyn should be concerned. Yes? Okay, because she's even lower than she was before. Now, I'm not going to change the height of these, and I'm not going to change the height of Brooklyn. I'm just going to tell Brooklyn, slide onto your desk. I will move with you. Now, all of a sudden, because I don't want to accidentally drop these things. Should Brooklyn even be remotely concerned now?
No.
But nothing has changed. She is basically where she was. These are only getting a little bit lower because my arms are getting tired. Why is Brooklyn no longer concerned? Because there's something in between. So now I'm not measuring all the way down to Brooklyn. I'm just measuring to the tabletop. Even though when she was here and so was I, and she was here and so was I, the distance between her head and these is the same. But now there's something that's going to stop it. So we don't measure to her face anymore. We measure to the tabletop. Thank you, Brooklyn. You get up. So where you measure the height from is absolutely relative. It depends on the circumstances that you're in. Nice try. No, gravitational potential energy. So, is there a circumstance where I'm standing right here with these two objects? Stop throwing goldfish. Don't encourage them to throw goldfish, unless you can guarantee that you'll catch them. Okay, you can throw one at Brooklyn, and if she misses, no more throwing at Brooklyn. Lots of pressure here. I'm going to call that an unsuccessful throw. Okay, actually, or an unsuccessful catch. Okay, so is there a circumstance where you would be concerned about me standing right here with my coffee cup and my highlighter if you were down a floor? No, because generally speaking, I mean, I could drop these forever, and we've got the layer of steel and concrete between us and them, or us and you, down on the second floor. Not a concern. If we talk about, even if we talk about our collective gravitational potential energy, if we're up, or when you have a class on the second floor, are you ever concerned about the class that's above you? Except when? You say no, you say yes. In the event of an earthquake, when the possibility exists that the stuff above you is going to come down upon you, then all of a sudden we get concerned. When you're in the third floor up here, you have less to worry about because there's less mass above us. But if you have a class on the first floor and you're in Mr. Jerome's room and there's an earthquake, now all of a sudden I would be shocked if the thought didn't cross your mind. What if? Because that would suck. But most of the time, the vast majority of the time, we don't think about it because it's not something to be concerned about. And if we're on the ones on the third floor, I mean, very rarely do we say to the people beneath us, my presence up here is going to suck for you. But in the event of an earthquake, it's going to be like, well, you guys are up. Because I'm up here, we are all collectively up here with a whole bunch of concrete and steel. And if we as a collective group of humanity in concrete and steel goes that way, everyone beneath us is going to feel the literal impact of our gravitational potential energy. But most of the time we don't measure to the ground because there's no good reason for us to expect to be moving towards the ground. And so we measure to tabletop or to the floor instead of all the way up. So you get to choose, but really, like, as far as the universe is concerned, whether the coffee cup in my hand gets measured to the floor or the second floor or the basement, like the ground floor level, as far as the universe is concerned, it's all the same thing. But as far as your experience goes, and as you observe these things, the impact of those things changes. Because in some circumstances, you don't need to worry about it. In other circumstances, you very much have to. So how much potential energy is available is dependent on some of those different things. So let's put some of that in here. The first one is, so this section here is all potential energy. Potential energy is the possible energy. Could something happen? Not how much will it hurt, but could it hurt? The possible energy of an object as a result of its condition or state or its position. So this thing right here, if you're unable to see what that is, that's a waterfall. Right here, at that location right there, there is a whole bunch of gravitational potential energy. Gravitational potential energy. Because is the water hurting you right there on the top of the waterfall? No. But if the water that was up on top of the waterfall made it down to you at the bottom, would it hurt? Yes. Yes, it would. A great deal. It is connected to the mass that's falling, the height it's falling from. The interesting part about the height is you get to choose how to measure. And the gravity at your location. A waterfall on the moon would be less concerning than a waterfall here on Earth. It would be extraordinary, yes. A waterfall on the moon would be amazing. Never going to happen, but amazing. Okay, so that is gravitational potential energy. What's that on the right there? A slingshot. No. Not yet. Soon, but not yet. So, slingshot. If you've never used a slingshot before, the primary operating mechanism for a slingshot is a rubber band. Well, what are these things? What's another name for these things? Elastics. So what kind of energy are we going to talk about here? Elastic potential energy. Now, elastic potential energy is the energy that's inherent in stretchy things. Different things stretch different ways. Your skin stretches, but no one's scared of that. I got two of these. Which of these, if you look at them closely, would you be most concerned of? The one on my right. Why? You're looking at this and you're saying it's thicker. What does the thickness of the rubber band have to do with making it scarier? It's got some mass, maybe? Okay. What else? Sorry? The impact? What were you going to say? The recoil is related to it. Like, if I had this guy here, and I pulled back, versus this guy here, and I pulled back, which one looked harder to pull back? The thicker one. And so that's really what you're concerned about. If I am successfully able to pull this thing back, but this thing is harder to pull back, when I point it at you and let go, it will probably hurt more. Because if it's harder for me to pull, it's going to collapse itself back quicker, probably. So that's part of it. The difficulty with which you are forced to pull in the rubber band is a function of potential concern. Let's forget the rubber band for a second. This is spring. Did I will use it? Okay, you grab that in. Okay, so don't walk. You stay right where you are. This is the spring at its rest. And I'm going to pull this spring just as much as I pulled the rubber band. No, you go get the move. Okay, back to 0. This is about the same distance I stretched the rubber band. Which one of these would be more concerning to you? Probably the rubber, because it looked like it was a lot harder for me to pull that elastic. Could you conceive of a possibility where this one would become the more concerning one? Sweet. Jedediah, go for a walk. Okay, stop. Just so all of you know where he is. You can't see him anymore. He is at the fire escape. So, keep going all the way to the recycle bin. Okay, cool. That's perfect. Love that. Please stop. This is gonna hurt. So, you can wait for the people to get out of the way. So now all of a sudden, this one was way easier. I don't know if you didn't see, I did. Jedediah had no problem walking out to now he's at the garbage cans. He relatively successfully, he just went for a walk. Now, if he were to let go of this versus the rubber band that I was pulling back, which of them is more concerning? This one's substantially more concerning because it's expanded way further. Okay, let go. Just let go. Right? Came back a lot quicker. Even though this thing was easier to pull because it was extended, thank you very much, because it was extended as far as it was extended, this one became the spring of larger concern. Okay? So elastic potential energy is directly connected to those two concepts. So let's label this. This is elastic potential. And elastic potential, the scariness of the elastic potential is related to two things. One, it's related to how hard is a spring to pull. The harder the spring, the more you should be concerned. Have any of you ever built a trampoline? Those springs are not very big. You cannot extend them very far, but oh my gosh. Every spring, my dad and I had to put our trampoline back together because you dismantle it for the winter so the snow doesn't wreck it. And it was difficult. Even to extend those springs a couple inches was really, really hard for me to do.
Yeah, they hurt if you get your finger caught in them. The scariest one I've ever seen was, so when I was a first aid attendant here at school, I mean, you guys generally, you think of like, oh, student gets hurt, first aid person gets called. What you guys don't ever think of, well, maybe, what you don't often think of, I'll say it that way, is what happens when a staff member gets hurt. Generally, when a staff member gets hurt, it's worse than when you guys get hurt. The worst one that I ever had to deal with was actually a Mr. Wimmer incident. For any of you who ever had a class with Mr. Wimmer, or you were on rugby or whatever, you know Mr. Wimmer. Mr. Wimmer's a tough dude. South African rugby player, the dude is tough. I got called after school to do first aid on Mr. Wimmer because he got his hand smashed in a shock that he was trying to disengage. So those are like a shock absorber on a car. Very, very strong springs, and he got his hand caught in one. And I watched Mr. Wimmer go into medically induced shock. Big, tough Mr. Wimmer went white, and then he went gray, and he could barely stand. And this was deeply concerning. He's a tough dude. So shock, like springs, the how hard it is to pull the thing is should be a deeply concerning piece of elastic potential. We call that, it has a name, we call it the spring constant. And every spring has one of these. It has a measure of how hard it is to expand or compress. And the harder it is to expand or compress, the scarier it should be for you. And then the other thing is what Jedediah demonstrated, it was the extension. And the extension is how far is it pulled from its rest length. Can we see that? Yes, we can. The further it's pulled from its rest length, the more concerning it should be. And so it's a combination of these things. Just like gravity was a combination of mass, height, and gravity, elastic potential is a combination of these two. And when we actually, we'll start to calculate these things. We'll look at them over the next couple days. We'll evaluate, we'll actually look at the numbers behind these things. But your intuition can be used for a lot of really good things here. You have an intuitive idea based on these concepts. I mean, whichever one's going to hurt more is the one that has more energy. When you're ready, flip the page. Okay, so those are the two major classifications of energy. We've got kinetic and we've got potential. There is more than just, well, when we talk about kinetic, we've got to break it down. When we talk about potential, there's more than just gravitational and elastic. So let's talk about all these things. When we're talking about kinetic energy, if you're talking about a generic object, a standard everyday object, everyday quote unquote normal object, what we're talking about is mechanical energy. Which is, it's using that word mechanical in kind of a different way. We're not talking about mechanics, Daniel and Massey. We're talking about just the motion of everyday objects. So like if you go to university and you take your first semester of physics at U of V, that course is called Physics 111. It's called mechanics. It has nothing to do with cars. It has nothing to do with putting things back together. That course is all about just how do normal objects move. That's all it is. Semester 1, mechanics. Semester 2 is these two. Actually, it's number 5. That's a plug. We already said that electricity is moving electrons, which is another kind of kinetic energy. It's electrical kinetic energy. It's the energy of electrons moving along a wire. That is semester 2. The entire 10-week course is all about electrons moving. It's way more interesting than it sounds. It's actually one of my favorite courses. Really, really cool. All of the crazy things that result. Going back up here, we'll jump to the next one. This is waves, specifically electromagnetic waves. So we call this radiant energy because electromagnetic waves radiate. Massey and Daniel. The most common electromagnetic radiation or radiant energy that you're familiar with is probably just visible light. That's on the electromagnetic spectrum. Let's say it's this middle part right here. This is your visible light. Which side of the visible light chunk looks more concerning to you? What does your intuition tell you? When it's more condensed, absolutely. If it's more condensed, more is going to be impacting you. This side of the electromagnetic spectrum includes things like UV, X-ray, and gamma ray. Those should all be deeply concerning. UV will cause skin cancer. When you go get X-rays at the dentist, they make you wear a lead vest, and the X-ray technician leaves the room. If someone's ever taking your picture and they're like, excuse me, I have to leave the room so the camera doesn't get me, you should be concerned. Not very many people go to the dentist or are scared of the camera, but how often do you think about the fact that they just left the room? Gamma, G-A-M-M-A. We'll talk about that in a couple days. We will talk about gamma. Gamma is a gamma ray, doesn't very often show up on Earth. Gamma rays show up on Earth when either stars close by explode or atomic bombs are detonated. That is when gamma rays are present on our planet. Those are the only two times that gamma rays are present on our planet. Infrequently, thankfully. When do stars explode? At the end of their life. If you let me get through physics quick enough, we can cram an astronomy unit in and I'll explain it to you. Okay, so this is the high end of the spectrum. It should be concerning. The left hand of the side of the spectrum is microwave. And within microwave, we're talking about things like cell and Wi-Fi. Your cell phone and the Wi-Fi signal is on the microwave side of the spectrum. Again, not concerning. I mean, it shouldn't be concerning because you are constantly being bathed in microwave radiation and nothing has happened to you. From birth, if there was Wi-Fi in your house or your parents owned a cell phone, if it was possible to get cell phone reception where you lived, or there was a Wi-Fi signal, you've been bathed in microwave radiation. You're fine. Even if you shoved your hand inside a microwave and got an intense blast of microwave radiation, yes, it would burn you, but you could get over it. If you got hit with enough UV and X-ray, you're going to get cancer and you will die. And if you got hit with a gamma ray blast, you would be instantly vaporized. These are more concerning. Even visible light's not without its dangers. I just need to increase the intensity of the visible light to blind you. There are flashlights that can do this. Yes. The distance light can travel in a year. Unrelated to this, but that's what that means. Okay, so the next one. Moving objects. Mechanical, radiant, thermal. Thermal energy, when we think of thermal energy, we often think of what? Four-letter H word. Heat. They are not the same, but they are related. See you later, Mahip. Enjoy your weekend. See you later. Thermal energy. If you guys remember back to middle school or elementary school, I can't remember where you would have learned it, but you would have learned about something called the kinetic molecular theory. The idea that everything in our universe is made up of particles, and then the degree to which those particle moves determines the state of the object. So your desks are solid because the particles there are just jiggling back and forth. If we increase their energy and allow them to jiggle further, now all of a sudden you have a liquid. If we ratchet up the energy and they're allowed to go wherever, now we have a gas. That's called the kinetic molecular theory, and at some point in your education, you were to have learned about this. Yeah, oh yeah. When we say theory in science, it doesn't mean it's a guess. It means These are the ideas that we put together that we know work. Again, another way we change the language on you. Theory is not it's not I wonder if, it's this is our best understanding right now and it works. So kinetic molecular theory, same thing. It's our current best guess, and to a degree, we know it works. Obviously, there's parts of it we can't guarantee, but that's natural selection. That was the whole point of us talking about natural selection. The idea that you can create, or that you can have different species show up out of, like, through natural circumstances. Now, that I did make a qualifying statement when we talked back in biology of we've never seen it on a scale as big as far as the theory goes, but we've seen it on a small scale. We have seen new species produced through environments on a small scale, and we still have no idea how life started. And we have no idea what the common ancestor is, but we know life on this planet is related. We just don't know how. Evolution happens to be our current best guess, and to a degree, we know it works. That's how there's so many variants of COVID, for example, because the virus is evolving. It's changing as generations pass. We just have never seen it on the scale of, like, big organisms. But we know it works on small organisms. Anyway, back to this. Thermal energy is related to the movement of those particles within an object. So thermal energy is the total movement of all of the particles. Heat is the average movement of the particles. And those are two fundamentally different things. Thermal is just the sum of the total. If I asked you for the sum of all the numbers from 2 to 5, the sum would be 2 plus 3 is 5, plus 4 is 9, plus 5 is 13. Well, let's go and include 1. That would be 14. So I added up 1, oops, that's the wrong thing. I added up 1 plus 2 plus 3 plus 4 plus 5, and I got 14. 15. 15. Come on, do we not figure that out? Thermal is just the sum. Heat is the average. So to find the average, what do you have to do to the things you just added up? Divide by the number of things you added up. So what is the average of 1, 2, 3, 4, and 5? Okay, the average, the sum of them, 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. But if I want the average of 1, 2, 3, 4, and 5, I add them up and I divide by how many there are. There's 5 numbers here. What's 15 divided by 5? 3. So 15 would be the thermal, the heat would be 3. This would be the average. So there's a fundamental difference there between thermal and heat, but they are certainly related. Number 4, what does number 4 look like? It's also movement. Sound. It's the vibration of particles. When you hear my voice, all you're hearing is the vibrations that my vocal cords have given to the air that are buzzing little hairs in your ear back and forth that your brain then turns into a signal. That's what sound is. It's the vibrations of the air. Let's see if we can crank out these guys before we leave today. That we've already talked about. This one is elastic. This one is chemical. We've talked about it already too. Chemical is the energy stored within chemical bonds. You guys get your chemical energy in the form of sugar. This one is what? What kind of potential energy is this? It's a falling apple. Gravity. Gravitational potential, stored energy due to the position of the object. This, what are those? Does anyone recognize those? What kind of power plant? That is a nuclear power plant. There is a ton of energy stored in the nucleus of an atom, and if you can get it out, oh boy, a lot of energy available to you. We'll talk about that in this unit. Can be. Doesn't have to be, but it can be. These are electropotential. The energy stored by the separating of positive and negative charges, because they want to get back to each other. Positives and negatives attract, and if you hold them apart, there's a bunch of potential energy there. That's how battery works. And then 6 is, that's a compass. Just magnetic, but yes. Magnetic potential. And we're going to talk about a bunch of these over the course of this unit. That's it. Bell's going to go in like a minute. You can pack up. No homework for you. Have a super duper day, and I'll see you, or have a super duper weekend. Enjoy the sun. I will see you on Monday.